The objective of this video is to practice laying out a double layer winding and to simplify winding factor calculations for double layer windings with constant coil span. And the second part of this means that all of the coils in our winding have the same coil span. And we've said that that is actually a condition of all the windings that we're laying out in this class. We're laying out lap windings, which by definition means that all coils will span the same number of slots. And so it's useful to take that into consideration for our winding factor calculations, particularly for double layer windings, so that we can reduce this down to a more manageable calculation. And we're going to do all of this by way of an example. So this video actually does not introduce much in the way of new content, but it works through an example problem that you'll find useful in the class. And in working through the example problem, I show you a way to make more efficient winding factor calculations for double layer windings. So we're going to do this by considering the design of a double layer winding for a stator that has 24 slots, 4 poles, and 3 phases. And the first part of this is that I want you to sketch the star of slots diagram and use it to assign coil sides to phases. So do step 1 in the double layer winding design procedure. So press pause, give it a try, and press play when you're ready to watch me do it. Since we have 24 slots, we know that our spacing between slots is going to be 360 degrees divided by 24, which is 15 degrees. And this means that our spacing between phasers is going to be our number of pole pairs times our slot spacing, which is 30 degrees. And we can use this to quickly sketch our star of slots. And this is the answer to question 1. You can see we've sketched the star of slots, and then we've used the star of slots to assign the top layer coil sides to phases. And we've done that by labeling our phase sequence going counterclockwise like we've been doing in the videos so far. Next, I want you to consider the design with different coil pitches. So remember, the second step in our winding layout is to determine the coil pitch, and that is how we know what coil sides in the bottom layer belong to which phases. So we've labeled our coil sides in our top layer up here, but then to determine what the coil sides are in the bottom layer, we need to have a coil, which starts in slot 1, wrap forward Y number of slots in order to determine where it returns in the bottom layer. And to do this step, I specifically want you to consider the first 7 harmonics of your winding factors for a full pitch coil, and then 2 options of short pitch coils. And before you go ahead and do this, I want to talk about winding factors. So this is the part of the video where we are going to talk about how to simplify winding factor calculations for double layer windings where all the coils have the same coil span. So let's start that by reviewing what we wrote out for our winding factor calculation from our winding factor video. And specifically, I want to write the expression that we had for our voltage phasor for a complete coil. And we'll talk about coil I and harmonic V, and that was equal to the difference between the voltage phasor of the 2 coil sides of coil I. So I'm noting here that this quantity right here is our voltage phasor for coil I, and that these 2 quantities are our voltage phasors for the 2 coil sides of coil I, coil side 1 and coil side 2, one of which resides in the top layer and the second of which resides in the bottom layer. And we had this expression. And so we interpreted this term right here as being our pitch factor. And we said that this is our pitch factor of coil I at harmonic V. Each of these angles here corresponds to one of the coil sides, and now we're going to note that one of the coil sides belongs in the top layer and the other coil side belongs in the bottom layer. It doesn't matter which you pick to be which, because you see that this quantity right here is just the average of the 2 angles. So alpha 1, we're going to say, is the angle of the slot of the coil side that's in the top layer. and alpha 2 is the angular location of the coil side in the bottom layer. Remember that our coil has a constant coil span, and we've been denoting the coil span angle as gamma. So we can note that alpha 2 is going to be equal to alpha 1 plus gamma. And so we can plug that into our expression for our pitch factor. That is, we can rewrite this making use of this expression as follows. And you'll notice that in this case, first of all, I've plugged this into this up here, and then I've rearranged terms until I had this expression where I separated out my alpha dependence to be its own exponent, and then I've got gamma in here. And you'll notice that I'm now indicating this alpha exponent as being alpha sub I to indicate that this is the location of our coil side in the top layer of coil I. Okay, so at this point, we can define this first term as being Kp0V. And I put the 0 in there, again, to indicate that it doesn't belong to any specific coil. It's just the pitch factor of our winding. That is, it only depends on the coil pitch. It does not depend on where that coil was placed. And when we multiply it by this exponent, now all of a sudden it becomes the pitch factor for a specific coil. So this is useful because we can plug it into our winding factor calculation to try to isolate the areas where the coil angle influences our calculation. And so I'll put this in blue because we're recalling this. This was a previous definition, that our winding factor is equal to the sum of our pitch factors. And we can then rewrite this by plugging in this up here into this down here. Till we get this final expression that I put in a box here. And we like this expression a lot because we've got in front, we've got Kp0V, which did not depend on the coil, the location of our coils. It just depended on the span of our coils. So this is a pitch factor. And then we have that multiplied by this quantity over here, where this term is the vector sum of the phase winding phasors in the top layer. And that's great because that means that we can use our star of slots that we sketched in part 1 to determine what our winding factors are going to be. We don't need to sum up all of the coil side phasors in the top and the bottom layer. We can strictly sum up the coil side phasors of just the top layer and then use our pitch factor to determine what the overall winding factor will be. So that saves us a lot of computation overhead. We can just consider the first layer, the top layer of our star of slots. And what we call this term, this entire term that I'm highlighting here, is we call this the distribution factor. You can see that in a double layer winding, in the approach we're taking in this class, we've parsed this out into a pitch factor and a distribution factor. This is different from what we did in the single layer winding, where we just looked at the winding factors being the sum of the pitch factor of each coil. Now in this case, we're parsing out our winding as having a pitch factor for the entire winding and a distribution factor for the entire winding. But at the end of the day, you should realize that this is the same definition of winding factor that we've been using all along. The winding factor is fundamentally this quantity right here. So it's the same fundamental physical definition as we had in our winding factor video. We've just written it in a form that's more convenient for calculations. And so we're now going to use that form to select our slot pitch. So our procedure for evaluating different slot pitches is that we do the following. First, we calculate KdV based on the star of slots of the top layer. So we perform this calculation right here. And then second, we pick a coil pitch that we want to test out, and we use it to calculate Kp0V, our pitch factor for that coil pitch for each of the harmonics of interest. And then third, we multiply our pitch factor and our distribution factor to get our winding factor. And when we want to try out a new pitch, we just circle back to step 2. We don't have to recalculate step 1 because step 1 is constant no matter what our winding pitch is. So at this point, you are ready to do this step 2 of of our winding design. I want you to go ahead, give it a try, construct a table that's comparing the winding factors for these three options. Press pause and press play when you're ready to watch me do it. So as a first step, I determined the pitch of each of our coils. And in part A, we have a full pitch coil, which means that our coil pitch is equal to YQ, where YQ is equal to M times our slots per pole per phase, and that gives us 6 slots. And then I converted this to the mechanical angle, or the mechanical coil span, which is pi by 2 radians. Next, I considered a coil that's been short pitched by 1 slot, so that is Y is equal to our full pitch coil minus 1. And if you note, this means that this coil has a span of 5 by 6, or 83%. And in our double layer winding design video, we talked about a rule of thumb where we want our coil pitch to be at least 80%. And so here you can see that we're approaching that limit. And that gives us a coil span over here. Next, I calculated the coil span for our second short pitch coil, which has been short pitched by 2 slots, so it has a span of 4 slots, or a coil pitch of pi by 3 radians. And this gives us a coil span of 67%. That is 4 divided by 6. So that, by a rule of thumb, would be too short of a coil pitch. Next, I'm going to write an expression for our distribution factor. And we just want the magnitude, so I'll put a magnitude symbol. And you can see that we're going to do this over, for the top layer, which is coil size 1, 2, -7, -8, +13, +14, -19, and -20. And if you look at this hard enough, you can realize that you can calculate your winding factor just based on your first revolution around this star, which is coil size 1, 2, -7, -8. You don't need to worry about the rest of the coil size because the winding is periodic. The winding factor will be the same if you calculate it incorporating those coil sides, or if you don't. And so we're going to take the easy path and just consider these 4 coil sides of 1, 2, -7, and -8. And since I'm doing it over just these 4 coils, I'll divide it by 4. And you'll see that I've written this out with our exponents having the harmonic value V for easy calculation later. I can just program this into MATLAB quickly or into my calculator. And remember that this distribution factor is going to be the same regardless of our pitch factor. So we just have to calculate this one time, whereas we'll be calculating our pitch factors separately for each winding. And the pitch factor is this expression. So for our full pitch coil, where gamma is equal to pi by 2, and remember that P is equal to 2, we get the following, which is going to just be equal to the sequence of 1, 0, -1, 0, 1, and so on. And so this is interesting because our coil pitch is always either has a magnitude of 1 or 0 for the full pitch winding. So let's go ahead and construct our table. So I'm going to fill in our table, and I'm going to do that by evaluating first this expression for V equals 1 through 7. And now I'm going to start considering each of our pitch options. And so I'll be calculating kWv by multiplying this column by this column. And since we're interested in the magnitude, not the sign, I'm going to erase these negative symbols and just report the magnitude. And next I'll calculate the pitch factor for our winding, which was short pitched by 1 slot. And again, I'll calculate our winding factor by multiplying this column by this column. So I'm going to shade in the winding factor column because that is what we really care about when we're comparing windings. And so for our full pitch winding, you can see that our fundamental winding factor was fairly high. It was 0.966 for the full pitch winding. But for the short pitch winding, it's been decreased slightly. It's now 93%, 0.93. So that's a modest decrease. But notice what's happened to our higher order harmonics. Our harmonics have uniformly decreased across the board. we've got 0.5 compared to 0.707. We've got 0.067 compared to 0.259. And again, 0.067 compared to 0.259. So this is a pretty good trade-off. We've lost a little bit of our fundamental winding factor, but we've also substantially decreased our harmonics. Let's now compare the final short pitch coil, which has been short pitched by 2 slots, and so that's the 67% span, which our rule of thumb tells us maybe is too short. And again, multiplying this column by this column to get our winding factor. And so now we notice that our fundamental winding factor has been quite significantly decreased, and our higher order harmonics have actually been increased. So this is clearly an inferior design. We do notice that one harmonic has been decreased, which is our third harmonic, compared to the third harmonic in the other windings. However, this harmonic actually does not matter. For a 3-phase system, the third harmonic does not end up producing any net field in the air gap as long as your phase currents sum to 0. So we don't really care what the value of this rho is, but we do care what these higher order harmonics are. And so we can see that our rule of thumb holds up in this case. This short pitch winding that's been short pitched by 2 slots is not as good. And I would say, by looking at these winding factors, this winding right here, short pitched by 1 slot, gives us a great trade-off. We've lost a little bit of our fundamental winding factor, but we've substantially eliminated our harmonics. So I'm going to pick this winding to go ahead and lay out. And the third task in here is to sketch the winding schematic for the y=5 design. So that is to sketch the winding schematic for this design. Please go ahead, give this a try on your own, and press play when you're ready to resume. But before you do that, I want to note that this is for phase U. So please go ahead and give this a try and press play when you're ready to resume. And so the way that we determine where our coils start is by going back to our star of slots diagram and noticing that phase U has got coil size 1, 2, 13, 14, 8, 7, 19, and 20. And then each of these coils is going to span 5 slots. And so finally, we have this winding layout. In summary, this video has worked an example problem for laying out a double layer winding, and then it's shown you a way to simplify your winding factor calculations for double layer windings in order to help you determine what the appropriate coil span should be. So we started by doing our 2 design steps for double layer windings. First, we constructed the star of slots and assigned coil phases, and then we use this elaborate procedure to determine the appropriate coil span, and we selected a coil span which has been short pitched by 1 slot. And then finally, we converted our winding design into a winding schematic.